Our next step is to add the code to open a WebSocket. To start, we'll include another library. You can include by typing it in manually. You can also include by using the Arduino IDE interface. I can't show that part of my screen, but I can show the effect of it. If I click on Sketch, go to Include Library, and then drop down to Contributed Libraries all the way at the bottom, you can see it'll include every header file that's part of that library. For our example, though, we really just need the WebSocket server.h file. Our WebSocket will also have some global state. And the only global state we'll keep around for it is the WebSocket itself and its port. Unlike the JAG code, here we're going to actually specify the port. And I should probably stick with more consistency here. Anything that's a constant global, I normally do as all caps. Now that we have our WebSocket server initialized, we can start it running in our setup function. And similar to the interface for Wi-Fi, we're going to call begin. But unlike in the case of Wi-Fi, we have a WebSocket object that we're creating instead of just some globally defined default one. If you're ever curious what a piece of functionality in your code does, I really highly encourage you to right-click on it, go to Definition, and we can see here that Wi-Fi is defined as just whatever the Wi-Fi class is. So here's our Wi-Fi class, which means it should have a static function called begin defined somewhere on it, or more likely, defined somewhere on one of the classes that it inherits from. And maybe it's worth just digging through and seeing if we can verify that that begin function exists somewhere. Not defined on any of those objects in a nice, easy to find place. I'll call that a failed search for now, and maybe that's something I'll loop back to if I get any questions on it on Slack. After we have begin, the most important part of our WebSocket functionality is to do something on events. So here in parentheses, we have to pass in a function that gets called whenever the WebSocket receives any sort of communication, whether that's a connection, data in the form of text, or binary data, or a disconnect. So we'll have to write a different function for that. For now, we'll just leave it as it is here, so that I can show you the next piece of functionality that's really important for WebSockets. And that's what we do down here in our loop. Not my favorite name for a method call, loop, because it doesn't actually loop, it's just the function you're supposed to call inside of your loop. So what this does is it says every time we loop through our code, we should let WebSocket update. So what it does when you call loop is it'll check the hardware interface, the Wi-Fi hardware interface, for any packets that have come in. And underneath the scenes, it'll call the event function that we pass in here. If you don't call loop, no communication will happen back and forth. So this is a case where it would be really bad to put a delay here. If I were to delay for a second here and turn an LED on and off, for example, we would just lose any packets that there wasn't enough space to buffer. So no delays inside your loop function. But now let's take a look at what we pass into event. We'll create a new function called WebSocket event. and I'll copy that over from my working code. And I'll copy over the header I created for it as well. So there's a pretty good amount of code here, but it shouldn't be too intimidating. It's essentially handling this connection that we see over here. So what do we do on a connect? Well, we'll have an event that comes into this function saying we've connected. And you can see I've not actually done anything here on a connect. On heartbeats, we'll set something to enabled and then disable after a timeout. And then on a disconnect, we'll want to make sure that we set something to disabled. Coming over here to our actual handler, you can see it takes a number of arguments. The first one is the client connection. So theoretically, we could have 4 or 5 different people or more connect to your microcontroller all at the same time, and they'll each have their own client number. In testing this, I really just connected once, and then I connected 4 or 5 times just to see how it handled multiple connections. In practice, you'll really just see this be a 1 each time. The type of event is either a disconnection event, a connected event, a text event, a binary event, or one of these other events that we're mostly just not going to handle. The next argument here is a pointer to a payload size. Whenever you see a uint8 pointer, that usually means you're pointing to a bunch of binary data. And then finally, the length of that data itself. This is a pretty common C idiom. Anytime you pass along a pointer that doesn't have a constant fixed size, you also have to pass along the length, so we know how much data is actually valid that's pointed to by the pointer. Let's take a look at what we do in the event that we receive some of these different types of events. On disconnected, I'm just going to print a message saying that the client has disconnected, and I'll also set a new global variable WSState to disabled. And that matches exactly what we have over here in our diagram. On a disconnect, we want to set our state to disabled. I have not defined either of these yet. These are things that we will define. This is not part of the library itself. On a connection, we're going to grab the IP address from the remote, so the client that's connecting, and print it out, and then just send a message back saying that, okay, we know that you've connected. None of that is strictly necessary, but it does help in debugging. The main type event that we can expect to receive are text events, so sending a string from, for example, the browser or a Python program that's connected over WebSockets. Here, I'm going to treat the payload as if it is a pointer to text and compare it to the word heartbeat. If my string comparison indicates that those are the same value, then this was a heartbeat, and I'll set our state to enabled, just like I have on the diagram over here. And we'll check, we'll mark the current time. So what was the last time that we had a heartbeat? This is another variable that we haven't yet defined that I'll have to define above. Any other type of text that we receive, we'll just print it out to the serial display. We're not actually doing anything with other types of data at this point. Same thing with binary data. This is something we'll look at later in the semester, but for now, we'll just print out that we received binary data and not explore it any further. Any other type of message is really just going to be an error for us. It could explicitly be an error, but we're not expecting to receive any sort of fragments. And that's the entirety of this function. I'm zoomed in quite a bit, so it looks like a pretty good amount of code, but there's just a handful of lines of code here. What is that? From about line 30 to about line 60. All right, let me bring over some of these other needed pieces of global state and update periods. The first thing that I'll do is I'll bring over an enum that I defined. So this is just a value of type WSState that can be in 2 different states, WS enabled state or WS disabled. This is how I'm indicating whether or not the entire microcontroller should consider itself as enabled or disabled. That doesn't introduce a variable, that's just a type, essentially. So, as part of our global state, we'll have our heartbeat. It's going to be of type WSState. And we'll start out in a disabled state. This is our first piece of functionality that's going to have an update period associated with it. And we really just need to remember two pieces of information. How frequently we need heartbeats to consider everything staying in an enabled state, and when was the last time we received a heartbeat. Now dropping down to setup, there's no additional work we need to do here for our WS state variable, but we do want to check it. So inside of our loop is where we check to see that we've received heartbeats. So we'll get the current time, and we'll see if the difference between the current time and the last time is greater than the heartbeat interval. If it is, we need to make sure we disable things, because that usually indicates a dropped communication, meaning we no longer have control of our microcontroller. At this stage, that's all the WS state is doing. Later on, we'll do something like if WS state is WS enabled, do something interesting. But we'll wait for that until the next video. For now, I want to make sure that this functionality works as is. But one thing I do before that is I'm going to add a couple of additional just debug printing statements into our setup code. I'm going to copy over the entire setup code here just to make sure I don't miss anything. All of this is code that we had before except for a few minor things. Initializing the serial interface to a specific baud rate, making sure we can connect to Wi-Fi. Once we're connected to Wi-Fi, printing off our IP address so that other users, for example, you could connect to it from your laptop. Initializing the WebSocket server and stating that the WebSocket server is running at this address. And finally, I copied over a bit too much. That's a preview for what we'll do in the next video. Last thing to do is to upload this code and see how it works. Again, I'll pause the recording here just so you don't have to watch this compile. The sketch compiled after a couple minor changes. I forgot that I capitalized SSID. And now it's uploaded. And you can see the output we have here. It connected to Pomona. Here's the address of this board, and here's the address of the WebSocket server. One last thing to try before the next video is to see what happens when we try to connect to this board. So we are able to connect, and you can see the first message down here is that there was a connection, and here's the IP address of my laptop. And I can send a message. And we can see that it got the text hello. And if I send a different type of message, for example, heartbeat, nothing will get printed, but the heartbeat after 1 second will time out, and we do get a print statement for that. So everything seems to be functioning at this stage. In the next video, we'll do something with this enable and disable functionality. In fact, we'll just turn on an LED, or more accurately, we'll put it into a blinking state.